We've spent a lot of time talking about exponents and logarithms. Now it's time to start talking about radicals, and these are very closely related to exponents because they are exponents. So if we have radical, you are familiar with right now as square roots. So if we have the square root of x, that is the same thing as x to the 1/2. If we have the nth root of x, that is the same thing as x to the 1/n. And we have some properties that we can apply just like we apply exponents, right? There's distributive property that we use. So in the distributive property, the nth root of a times b is the same thing as the nth root of a times the nth root of b. Okay, in other words, for the same reason, just using square roots, okay? And if you notice, I put these little tails here just so that it's clear that the the radical ends after the a, okay? So you can always put a tail on your radicals just so that it's very clear where they end. If we had, for example, the square root of a times b, if you think about it in terms of exponents, that's the same thing as a times b to the 1/2. And we can distribute an exponent. It becomes a to the 1/2 times b to the 1/2, which is the same thing as square root of a times square root of b. We can distribute with multiplication. We can also distribute with division. So if we have the nth root of a over b, then this is the same thing as the nth root of a over the nth root of b. Okay, so if we put in a number and we say, okay, well, what about the 5th root of 32, for example? Now, if you know your radicals really well, then this may not be that difficult for you, but a lot of people don't. So if we needed to put this into a calculator, one thing that we can do is we could say, okay, well, this is the same thing as 32 raised to the 1/5 power, and that's equal to 2. Now, just to be really clear about this, what we mean by the 5th root of 32 is what number could be multiplied by itself 5 times to get to 32. And we're saying it's 2 because 2 times 2 times 2 times 2 times 2 is equal to 32. Okay, now on your calculators, sometimes you'll see the caret. You're just using your exponent, and just make sure that when you're putting it into your calculator, you're putting the 1/5 in parentheses. Okay. Okay, so a little bit of vocabulary here. If we have the nth root of x, okay? Nth root of x. The n over here is referred to as the index, okay? So this is the index. Over here, the index is equal to 5. Okay, that's the index. The x is the radicand. That's what is under the radical. And this symbol is just a radical. Okay, this vocabulary is important because sometimes it's a lot easier just to say radicand rather than, oh, well, what's written under the radical? Okay, and you can't say square root all the time because the only time that you have square root is when you do not see an index. Okay, when you do not see an index. So this is the nth root of x because the index is n. Okay, and we talked about how if there is no power, it's a power of 1. If there is no base in logs, it's a base of 10. This is the same type of thing. We use the square root more often than any other root. So because of that, if there is no index, then it is an index of 2. So just to clarify, the index is what is outside of the radical. It's what's inside the little v, and you need to be careful, okay, in terms of handwriting. It needs to be very clear what the index is. You don't want it to look like a coefficient. You are not multiplying the radical by this number. This is indicating what root it is. It is giving you more information. It is not a multiplication, okay? The radicand is what's under the radical, and the radical is simply the symbol itself, okay? Okay, we're going to start simplifying radicals, but in order to do that, it is helpful to know some of your powers, okay? It can make things go much faster, just like knowing your multiplication tables can make things go faster. So the ones that I would become really familiar with if I were you is powers of 2. So 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. I would even go as high as 2 to the 6th is 64. For your powers of 3, I would know 3 squared is 9. I would know that 3 cubed is 27. 3 to the 4th is 81. And 3 to the 5th. Actually, you probably don't even have to go up to 3 to the 5th, but 3 to the 5th is 243. I would know that 4 squared is 16. And 4 cubed is 64. Those are the big ones that I would know. So if I were you, I would set up a set of flashcards, and I would just memorize this. You could always figure it out, but it is just much faster if you know it. Okay. Okay, so let's start with simplifying. This is much simpler or much faster than simplifying logarithmic expressions or exponential expressions. Okay, and this is really when the index is not equal to 2, because when the index is equal to 2, you can't simplify it any further. Okay, so specifically for when the index is not equal to 2. And remember, the index is n. Okay, when the index is equal to 2, you cannot go any further. You cannot simplify further. So just like everything else that we've done, there are 2 things that you're checking for. There should be no fractions in the radicand. Only integers. And I'm going to include here no radicals in denominators. This is not going to apply for now. This will apply when we get to operations on radicals, so that's why I'm putting it in there. Second thing that you want is that the rational exponents are all less than 1. And this is if we were to convert the radicals to exponents. So you'll understand what this means as we go through different examples. Okay. So let's take a bunch of examples and work through it, okay? First example, the cube root of x to the 6th y to the 3rd. So I'm going to do this in a long way. You can actually just jump right to the last step actually, okay, as you start to get accustomed to doing this. So this is a case where I'm showing a lot of work in the beginning for your benefit, and then you can just sort of just jump to that last step. So we have x to the 6th, y cubed, and this is really being raised to the 1/3 power. Okay, so this is what we mean by taking the radical and turning it into something exponential, right? On the last page, what we did is we said, okay, if we were to convert the radicals to exponents, okay? So we're converting the radicals to exponents right now. Now we can just distribute this, right? That 1/3 power can be distributed. And when we distribute the 1/3 power, and I should put this in red, I apologize. We get x to the 6/3 times y to the 3/3, which is just x squared, y to the 1st, and typically we would not write y to the 1st power. We would just write y. Okay, so a couple of things to note here. The first thing is that because we could take away the radical completely, This is a perfect cube. This is a cube root. This is a perfect cube. Okay? Sorry, this is a perfect cube. What is under the radicand? Okay? And I'll write that down in a second. I want you to notice something else. Essentially, what we did here is we took our exponents that are under the radical and we just divided them by the index. And because they were divisible by the index, that's what gave us the cube root, which we know is a perfect cube because they are divisible by the index. Let me repeat that. What we did is we took the exponents that were in the radicand and we divided them by the index. Because they were divisible by the index, this is a perfect cube. Okay, so let's write that down. All you have to do in order to simplify a radical like this is you're going to divide the exponents in the radicand by the index. And then a note, if all the exponents are divisible by the index, meaning your answer is an integer, the radicand is a perfect nth root. Okay, x to the 6th, y cubed I don't mean root here. This is a perfect cube, a perfect, if this were 2, it would be a perfect square. If this were 4, honestly, I'm not exactly sure how we would describe it. It would be a perfect 4th. So if this were 5, it would be a perfect 5th. So what we're saying here using this example is x to the 6th y cubed is a perfect cube. Okay, so we're going to keep doing this by example. Okay, so notice what we did here. We could go right from this first step to this very last step, x squared y. You can skip everything in the middle. And that's what we're going to be doing with the next one. We're going to skip everything in the middle. So we have, in this case, the square root. The index is 2. Square root of x to the 14th, y to the 10th. So what is this? You should try and do it on your own. Here is our exponent. Our index is 2. So we just divide the exponent by 2. This is x to the 7th. We divide our exponent by 2 because 2 is the index. So 10 divided by 2 is 5. So this is x to the 7th, y to the 5th. So again, take each exponent and divide by the index. (14 over 2 is 7. 10 over 2 is 5. And as a result, we were able to get rid of the radical because this is a perfect square. Okay, let's add a little bit to this. Let's take a case where we have an integer, a constant, under the radical in the radicand. So let's take the fourth root of 16 x to the 28th, y to the 20th, z to the 16th. Okay, so how do we do this? Exactly the same way. So we're going to have an equals. Start with the variables. So x to the 28th is going to become x to the 7th. Y to the 20th becomes y to the 5th. And z to the 16th becomes z to the 4th. But now we have the 16, Sorry, this is a 5. Okay. I'm going to erase that and do it one more time. Okay. We still have the 16 though. We have to take the fourth root of 16. So you're not dividing by 4. You're taking the fourth root. And this is why I said that knowing your powers can be really helpful. The fourth root of 16 is 2. So you're looking at an exponent of 4. Okay? You want to know what number raised to the fourth power is 16, and it's 2. So this final answer, and I'm going to box this because I forgot to put it in red. Sorry about that. This is your final answer. And we get this because 2 to the 4th is 16. So 2 to the 4 equals 16. That's where the 2 comes from. Then we did 28 over 4. That gives us 7. We did 20 over 4. That gives us 5. And we did 16 over 4, which gave us 4. So for everything else, you're dividing. But for the integer, you're finding the fourth root. Okay? So let me just write that down so that it's clear. 16, this 16, is not an exponent. So you wouldn't divide by the index. Only exponents get divided by the index. Okay, if it's a constant, then you're finding the nth root, in this case, the fourth root. Okay, let's do another example. Sorry, I'm just plugging in the pen so that it charges. Okay, let's do another example. Let's say that we have the cube root of 64x to the 12th y to the 21st. Okay, I'm gonna change the color. I think it matters because I think in the notes it's helpful for you to see what the problem is, for that to not be confusing. So the cube root of 64 x to the 12th y to the 21st. And this should be pretty straightforward by now, with the exception of this integer. So in this integer, we have the 64, right? And we have to take the cube root of 64. So the cube root of 64 says what number can you raise to the third power to get 64? And the answer is 4. Okay, 4 to the third is 64. Then we take the exponents and we divide by the index. So we get x to the 4th, y to the 7th. So again, to be clear, 4 to the 3rd is 64. 12 over 3 is 4. And 21 over 3 is 7. That's where we got these answers from. Okay. We're going to make this a little bit more complex now. What if it's not a perfect nth root? Okay, in all of these cases, 1 through 4, our answer didn't have any radical in it at all. But that's actually rarely the case. So let's see what happens when it's not the case. Let's start with the square root So notice there is no index, which means that the index is 2. Square root of 12x to the 7th, y to the 9th. Okay, in this case, it is a two-step process. So we're not really making it so much more complex in terms of the amount of work that we do. All we're doing is we're taking what would be, we're just splitting this up into what is a perfect square and what is not a perfect square, okay? And what we're really doing is we're trying to find factors of each of these numbers that are perfect squares. So like, for example, let's take 12 because that's a number and that's easy to see. 12 is not a perfect square, meaning there's no number that we can multiply by itself to get to 12. But what we're looking for is there a factor of 12 that is? And the factors of 12 are 2 and 6. Those are not perfect squares. And 3 and 4. Now 4 is a perfect square. So what we're going to do is we're going to split this up into two radicals. The first one is going to be a radical that is a perfect square. And the second one is going to be whatever is left over. Okay. So 4 is a factor that's a perfect square. So 4 is going to go over the first one. And what's left over? 3 is left over. Because remember, these are getting multiplied. The rule that we're using here is this one, this distribution rule. We're saying we could take something and we could split it up into two radicals that are being multiplied together. So if these are being multiplied, then we could split it into two radicals. Here, 12 is the same thing as 4 times 3, so we could split it into two radicals. One that has the 4, which is a perfect square, and one that has the 3, which is not. Okay, now for the exponents, it's a little bit different. For the exponents, we want to figure out, okay, well, we need an exponent that's a perfect square, meaning it's divisible by 2, right? Perfect square means it's divisible by the index. So we need an exponent that's a perfect square, and then we're going to have whatever is left over. So you're going to start here, and you're going to say, okay, well, 7 divisible by 2. It's not. So then go down by one number. 6. Is 6 divisible by 2? It is. So x to the 6th is going to go under here. What's left over? Well, we took away 1x, so x to the 1st is left over. Okay? So you're starting at the 7. You're saying, is it divisible by the index? If it's not, go down by 1. We have 6. Is 6 divisible by the index? Yes. So we're going to put x to the 6th under the perfect square. And then the remaining x's that we took away, which is just 1, we're putting that in the second one. Okay? Now we're going to do the same thing with y to the 9th. We look at the exponent and we say, is it divisible by 2? It's not. So we go down by 1. 8. Is 8 divisible by 2? Yes. So under here is going to be y to the 8th. What's left over? Just a y to the 1st, because 8 plus 1 is 9. The sum of the exponents has to equal the exponent that's under the radicand. Okay? So what do we get here? Well, what's under this radicand, we can't do anything with. It can't be simplified anymore. Again, this is what I meant by the second one. The rational exponents are all less than 1. If we were to take this and remove the radical, it would be 3 to the 1/2, x to the 1/2, which is a number less than 1, and y to the 1/2, which is a number less than 1. If we were to remove the radical here, it would be x to the 6/2, and 6 over 2 is not less than 1. So we have to simplify this, okay? So this is a perfect square. The square root of 4 is 2. The square root of x to the 6th is x to the 3rd. We divide the exponent by the index. And the square root of y to the 8th is y to the 4th. 8 divided by 2 is 4. And then the square root of 3x to the y just gets left alone. Okay, let's write some of this down. For these variables, okay, let's do this in 2 steps. For the constant, meaning the 12, for example. In the previous problem, in problem 4, it was 64. In problem 3, it was 16. Problems 1 and 2 don't have constants. So for the constant, we are finding the biggest factor that in this case is a perfect square root. But if we want to generalize it, a perfect nth root. Okay. For the variable, you want to find the largest number less than or equal to the exponent that is divisible by the index. And we're saying that the exponents for each variable should add to the exponent in the radicand. And when I say that, I'm referring to what you see broken up in these two sections. So for example, the exponents of x are 6 and 1. When we add that, we get 7. The exponents of y are 8 and 1. When we add that, we get 9. Okay, so let's do a few more of these so that you get the hang of it. But once you get the hang of it, this is a very fast process. And I will tell you that if you look this up online, you will never see a process this simple. You will see it broken up into lots of different steps, and it's going to be far more time consuming. Okay, so I do encourage you to really pay attention to what's going on here, because this is just a two-step process. Okay, you're breaking it up into a perfect nth root and then whatever is left over. Okay, so let's take the cube root of a to the 6th, b to the 10th, c to the 5th. So we're going to break this up into two roots. Root where it's perfect cubes, and then whatever is left over. And I would do this one letter at a time, one variable at a time. Okay, so your first one, these are going to be your perfect cubes. And then this is just what's left over. Okay, so let's start with the A. So remember, you want an exponent. You want a number. You're looking at the exponent and you're saying, what's the greatest number less than or equal to 6 that is divisible by 3? So start with 6. Is 6 divisible by 3? Yes. So that's it. The whole a to the 6th goes under here. And there's nothing left over. Okay, let's do the B. So we look at the 10. 10 is not divisible by 3, so go down by 1. 9. 9 is divisible by 3. So that means that b to the 9th is a perfect cube. What's left? Well, we still have 1b left over. 9 and 1 is 10. Okay, let's do the C. Is 5 divisible by 3? No. So we go down by 1. Is 4 divisible by 3? No. We go down by 1 again. Is 3 divisible by 3? Yes. So C cubed goes under the perfect cubes. What's left over? Well, we used 3 of the C's. There are 2 left over. And we know that this is correct because 3 plus 2 is equal to 5. That's our first step. Second step, simplify this. So take every one of these exponents and divide by 3. So what do we get? 6 divided by 3 is 2. So we have a squared. 9 divided by 3 is 3. So we have b cubed. And then 3 divided by 3 is 1. So we just have c. And we still need to keep this cube root of b times c squared. And I'm going to emphasize again, please make sure that your 3 looks like an index. Okay. Let's take another one. And this one, I would recommend that you try it yourself. Okay. Okay, let's take the 6th root of 64, x to the 8th, y to the 26th, z to the 13th, a to the 38th, and b to the 41st. Okay, it looks complex, but it's only 2 steps. So our first step is we have the perfect cubes, the perfect 6th roots, perfect powers of 6, and then we have what's left over. And hopefully I left enough room. So start with the 64. So remember, 64 is an integer. It's a constant. So when we look at the constants, we're finding the biggest factor that's a perfect nth root. That's a perfect cube. I shouldn't say nth root. Keep doing that. Okay. Factors of 64. Well, we have 8. But that's not a perfect 6th root. That's a perfect square. It's got to be a relatively small number if 8 is a perfect square, meaning 8 times 8 is 64. You need something multiplied by itself 6 times is 64. And there is a perfect 6th root. It's 2. So 64 itself is perfect. And there's nothing left over. Then we have x to the 8th. So we need a number that's divisible by 6. So we start with 8. It is not divisible by 6. Go down by 1. 7. No. 6. So 6 is divisible by 6. So x to the 6th goes under here. And then we have to say, okay, well, what's left over? There are 2 x's left over. I'm going to move this over just a little bit because I don't think I gave myself enough room. Okay, so if you have x to the 6th, what's left over? 2 x's. We used up 6 of them, there are 2 left. Now let's do the same thing with the y. 26 is not divisible by 6. 25 is not divisible by 6, but 24 is. So what's left over? 2 of them. You're never going to have more than 5 left over, because if there's more than 5, then you're going to have a larger number under here. Sorry, I don't know why this 2 isn't really coming out. Okay, z to the 13th. 13 is not divisible by 6, but 12 is. So we're going to have a z to the 12th here. What's left over? Just 1 z. Okay, a. So a has power of 38. 38 is not divisible by 6. 37 is not. The 36 is. So we're going to have an a to the 36th under here. What's left? 2 a's. So we're going to have an a squared. Okay, and finally the b. b to the 41 is not divisible by 6. 40 isn't, 39 isn't, 38 isn't, 37 isn't, 36 is. So we could have a b to the 36 under here. What's left over? 5. 36 and 5 is 41. Okay, so now the only thing left is to simplify this first square root. So the sixth root of 64 is 2. 2 to the 6th is equal to 64. We're going to take each of the exponents and divide by 6. 6 divided by 6 is 1, so it's just x to the first. 24 divided by 6 is 4, so we just get y to the 4th. 12 divided by 6 is 2, so we get z squared. 36 divided by 6 is 6, so we have an a to the 6th, and for the same reason, a b to the 6th. And now we just have the 6th root that we have to write. And under that radical is x squared, y squared, z, e squared, b to the 5th. That's a 5 there. Okay, and that's it. Let's do another one. Let's do the 5th root. Of 64. A to the 21st, b to the 33rd, and c to the 20th. Okay, so once again, we're splitting this up into 2 radicals. One is going to be with perfect fifths, and the second one is going to be what's left over. Okay, the constants are really the hardest because constants, being familiar with it, can be really helpful. Again, this is a 5th root, so you know that it's got to be a number that's small. But look at the factors of 64. 64 is not a perfect 5th. It's a perfect 6th, but not a perfect 5th. So what are the other factors of 64? Well, we have 4 and 16. Those are not perfect 5th roots, right? 4 is a perfect square. 16 is a perfect square. It's also 2 to the 4th, but we need something raised to the 5th power. Then we have 32 and 1. 32 and 1 is, we have 32 and 2. So 32 is a perfect 5th. 32 is 2 to the 5th power. So 32 is going to go under here. What's left over? A 2. Remember, the constants multiply to what's under the radicand. The exponents add, the constants multiply. Then we do each of our variables. So we're going to have an a to the 20th under here. 21 is not divisible by 5, but 20 is. Which means that we're going to be left with an a to the 1st. Then we're going to have a b to the 30th. 33 is not divisible by 5. 32 is not. 31 is not, but 30 is. Which means what's left over? 3 b's are left over. 30 plus 3 is 33. And the whole c to the 20th goes under the first one because 20 is already divisible by 5. Okay, so now we just have to simplify. 2 to the 5th is 32, so that's 5th root of 32 is 2. 20 divided by 5 is 4. 30 divided by 5 is 6. We already said 20 divided by 5 is 4. So now this is the coefficient of the radicand, of the, coefficient of the radicand, of the radical. And then the 5th root of 2ab cubed. Okay, I apologize. I know sometimes these numbers don't come out so well. That's why I say it. Okay, let's do one last one, and then that will be it. And again, this I would strongly, strongly, strongly recommend that you try it on your own first. Let's do the 4th root of 243 a to the 17th, b to the 23rd, c to the 42, and d to the 20th. This is a 23, not a 73. Sorry about that. Still didn't come out. I don't know why this 2 is not coming out. There we go. Okay, so what does this equal? We're going to split this up into a 4th root where it's a perfect 4th. And then into whatever is left over. So the 243 may take some trial and error, but this is where it comes in handy to know things like this. Okay, 81 is a perfect 4th, and 243 is 81 times 3. So the factors of 243 are 81, which is the perfect 4th, and 3. Notice they multiply to 243. And it takes just a little bit of trial and error. You're looking for what are the factors of 243, and then once you find the factors, raise them to the 1/4 power, right? You can do that in your calculator and see if you get an integer. Then we have the a. So we're going to have a to the 16th. 17 isn't divisible by 4. We go down by 1. 16 is. Which means that under here, we're just going to have a to the 1st. 16 and 1 is 17. For the b, it's got to be b to the 20th. I don't know why these 2's aren't coming out. The computer clearly does not like my 2. Okay, that's a 20. Which means that we have 3 b's left over under here. Okay, c to the 42. 42 isn't divisible by 4. Neither is 41, but 40 is. What are we left with? A c squared. And then the entire d to the 20th goes under this first radical because 20 is divisible by 4. And now the only thing left to do is to simplify this first radical. So the fourth root of 81 is 3. 16 divided by 4 is 4. 20 divided by 4 is 5. 40 divided by 4 is 10. And again, 20 divided by 4 is 5. And then the second radical gets left alone. It's just the fourth root of 3ab cubed c squared. That's a b to the third power. And that's it. This is how we simplify radicals. And in our next video, when we do operations on radicals, this is going to become really critical.